Welcome to science class. Today, we will be investigating earthquakes and learn what they are, why they happen, and how they are detected. The study of earthquakes is called seismology, and it's a recent discovery. It was totally unknown why earthquakes occurred until the 1960s. I have an earth science book that is copyright 1901. In here, the author describes what earthquakes are, and the author also describes the patterns we see in the geology of Earth that arise from plate tectonics, but there is no explanation for how earthquakes occur. The entire topic of earthquakes is confined to just one paragraph in this book. Earthquakes are impossible to predict, but they do occur in predictable places, at the boundaries of tectonic plates. Again, nobody knew about tectonic plates until recently. So, as it goes, earthquakes were explained as events that have an agent behind them. The gods are mad at us. Last year it was a plague. The year before that, the big volcano erupted. The year before that, it was a drought. This year we did something wrong. Now they've punished us with an earthquake. The first real attempt in trying to learn something scientifically about earthquakes came after the 1909 San Francisco earthquake. This earthquake struck with a magnitude of 7.9 and destroyed over 80% of the city. The majority of the destruction was caused by fires, not the actual earthquake itself. It still ranks as the deadliest natural disaster in California's history with over 3,000 deaths. After that event, the few seismologists there were in the world developed a few important ideas. One was what's called the elastic rebound hypothesis, which we will cover after a little while in this video. The other was they connected earthquakes and faults. Seismologists observed that after an earthquake occurred, areas around faults changed. If there was a fence out in the country, for example, that fence would now have a kink in it after the earthquake. This meant that not only does the surface vibrate, apparently it moves. That was a big clue. Let's get started. This video will not be a history lesson on the development of seismology. It is a science lesson on seismology. In the future, we will learn the details of plate tectonics, but what you need to know to understand earthquakes is that the solid surface of Earth, the lithosphere, is broken into enormous fragments called tectonic plates. These plates move slowly. Almost all earthquakes occur where two plates meet. At some of these boundaries, the plates are moving towards each other. At some boundaries, they are moving away from each other, and at other boundaries, they are sliding past one another. The movement of these plates is not continuous. Plates move on average 5 centimeters a year, but like I said, it's an average. A section of the plate might not move at all for hundreds of years. Then during one particularly violent earthquake, it moves an entire meter. It's also not the entire plate that moves, but small regions of the plate. That's why earthquakes happen in specific locations. If the entire east border of the Pacific Plate moved 20 centimeters, that would cause the complete destruction of all civilization on the west coast of North and South America. What happens is, as two plates push into one another, they build up stress. Stress causes strain, which is the deformation of material. I apply stress, a force, to this ruler, and it strains and deforms as a result. An earthquake occurs when the strain goes past the flexibility of the material and the material breaks, releasing all of this stored potential energy. This is what causes the earthquake, and the entire mechanism I've just described is known as the elastic rebound hypothesis. A powerful enough volcanic eruption can also cause an earthquake, but more than 99% of earthquakes occur because of the sudden release of built-up elastic energy within the lithosphere. The point within the Earth where this movement and release of energy occurs is called the focus. Most earthquakes begin several kilometers below the surface. The epicenter is the point directly above the focus, which allows us to map where earthquakes occur. Maps of earthquake epicenters were the first overwhelming bit of evidence that tectonic plates exist, because a map of these epicenters shows us they are not randomly distributed. Instead, they create a sort of puzzle on the surface of the Earth. Each piece of the puzzle turned out to be a tectonic plate. Energy travels in waves, and two kinds of waves are released from the focal point during an earthquake. One group of waves are called body waves. The first type of body wave is called a primary wave or P wave, and it is a compression wave. Compression wave means that the wave travels in a back and forth type of motion. If you have a spring and you compress the spring, then let go, that compressed region will travel down the spring. The P wave travels through a material by altering its density. That's the nature of compression. They're called primary waves because they have the highest overall velocity of any seismic wave, around 5,000 meters per second in granite. They also carry the least amount of energy. The other type of body wave is called a secondary wave or just S wave. S waves are transverse waves, which in simplest terms means they transfer through material in an up and down or side to side motion. S waves carry more energy than P waves, they move slower, and they can only travel through solid materials. The other major group of seismic waves are surface waves. Surface waves also transfer energy transversely, meaning they cause the Earth to deform in an up and down way, making the Earth's surface behave more like a fluid during an earthquake. Surface waves carry far more energy than body waves do, so they are responsible for almost all of the damage. They are also the slowest moving waves. They have a little more than 53% of the velocity of P waves, meaning they're about twice as slow. This difference in velocity is how we detect where earthquakes occur. Let's say we have two cars. Both of them take off at the same time, one going 100 kilometers per hour, the other going 60 kilometers per hour. We can make a graph that would show how far apart the two cars become over time. The same principle applies to seismic waves. We know the velocities of each wave. A seismic station will detect a noticeable gap between the arrival of the first P wave and the secondary S wave. The greater the gap between them, the farther away the earthquake began. Using a travel time graph, we locate the difference in time between the waves, and then we find the distance to the epicenter. But we don't know which direction. All we can do is draw a radius. However, as long as you have 3 seismic stations, each measure the same earthquake, the 3 radii or circles they draw will intersect at exactly one location. This is how we find the epicenters of earthquakes. As I mentioned earlier, mapping the epicenters of earthquakes showed that they occur in predictable locations, which were later revealed to be the boundaries of tectonic plates. That's where we will end with earthquakes for today. Next time, we're going to discuss how the energy from earthquakes is detected and measured, and the dangers associated with earthquakes. Thanks for watching.